I have here some interest review problems, and these problems are not the same as those on the mastery or unit test, but they are similar and they will help you with the mastery test and the unit test. We're going to talk about them in order of difficulty. So we're going to start with the simplest one, simple interest. When you're calculating simple interest, or thinking about simple interest, you can think about the simple interest formula. I'm going to look at the guided notes. And on the second page, it talks about the simple interest formula. I equals P times R times T. And you should have written down I equals interest, P equals principal, R equals annual interest rate expressed as a decimal value, and T equals number of years. So here in this problem here, it's asking us to calculate the interest earned on each simple interest account, given the original principal, annual interest rate, and length of time the account was held. So here I have 3 different accounts with 3 different principals, and principal is the amount of money that you started with. So that's going to be this amount of money right here. That's the original principal. $2,500, $550, $352. I also know the annual interest rate. So for this account, it was 4.3%. For this account, it was 3.12%. And for this account, it was 2.7%. And I know the length of time that the account was held. So for one account, 2 years, for one account, 3 years, and for one account, 5 years. So let's look at this a little bit more. At the top of my page here, I'm going to write down my simple interest formula, that equation that tells me how to calculate simple interest. I have interest equals principal times the annual interest rate times the amount of time the account was held. For each of these problems, to help me stay on track, I'm going to recopy this formula. I'm going to start with this first problem here. So interest equals principal times rate times time. And I'm looking to calculate the interest earned on each simple interest account. I'm not looking to see the total amount that the account had after that amount of time. I'm just looking to see the amount of interest that was earned in that amount of time. So then I can use just this formula because it tells me just the amount of interest that was earned. So I'm going to put in the information that I know. Interest equals principal, which is this 2,500, times the rate. So I know that the rate equals 4.3%. Percent tells me how much you get for every $100 you have. So per 100. So in this case, for every $100 that I have in the bank, I would get $4.3 or $4.30. I can rewrite this per 100 as 4.3 over 100, or divided by 100. 4.3%, cents like 100 cents in a dollar. Now, I want to convert this to not a percent, not a fraction, but a decimal. And in order to do that, I'm going to move the decimal on the top and the bottom of the fraction. If I have a whole number, my decimal will be right here. That's the end of my whole number. I don't have any numbers in the decimal place. I'm going to move this decimal over 2 places so that my fraction is over 1. and then that, or divided by 1, and then that will, anything divided by 1 is itself. So when I move over this decimal, I'm moving over 1 decimal place and 2 decimal places, but I have this space here. So what I'm going to do to keep this 4 in that second decimal place, which is the hundredths place, I'm going to put a 0 here in the first decimal place, which is called the tenths place. And then I can rewrite this as a decimal, 0.043, or 43 thousandths. If I wanted to, I can also put a 0 in front of my decimal, but I don't have to. So now I can plug in this decimal value into my equation. So I have my principal, $2,500, times the rate as a decimal, which is 0.043, times the amount of time that the account was held, which in this case is 2 years, the number of years. So that's times 2. And now I am going to use my calculator to calculate this. $2,500 times 0.043 times 2. Although you could calculate this with long multiplication, I don't expect you to. You can use a calculator. That's not cheating, it's using your resources. So I equals $215. We're going to do the same process for this account. This account had $550 at an annual interest rate of 3.12% for 3 years. So I'm going to write down my simple interest formula. I equals principal times rate times time. And I'm going to plug in the information that I know. So interest equals $550 times the rate. My rate equals 3.12%. 3.12% per 100. Move this decimal place over 2 places to the left when I'm converting a percent to a decimal. 1, 2. My new decimal place is here, and I need to put a 0 to hold my place. I can rewrite it as a decimal point. 0, 3, 1, 2. I can plug that into my formula here. 550 times 0.0312 times 3 years. And then I'm going to calculate on my calculator. 550 times 0.0312 times 3 years is $51.48. That's going to be the amount of interest that was earned in this account in 3 years. And finally, an account that had $352 at a rate of 2.7% for 5 years. Again, I'm going to write my simple interest formula. Interest equals principal times rate times time. And I'm going to plug in my information that I know. Interest equals $352 at a rate of 2.7%. That's 2.7 per 100. Move this decimal place over 2 places. Move this decimal place over 2 places and put a 0 to hold that place. 0.027 is my rate, my interest rate expressed as a decimal. So I have interest equals 352 times 0.027 times 5. And I'm going to calculate that. 352 times 0.027 times 5 equals my interest earned is $47.52. Now I'm going to look at some exponential expressions. And when I talk about simple interest tells me that every time I earn interest, I earn the same amount of interest because I'm earning interest on the principal, and it's the same percent every time. So in the case of this one, I'm going to earn $215 every 2 years. So the first 2 years I earn $215 with the same amount of principal. The next 2 years I earn $215. The next 2 years I earn $215. And it goes on in a straight line. This is called a linear expression. Simple interest is linear growth. It grows in a straight line. Exponential growth tells me that it's not growing the same amount each time. It's going to grow a little bit, and then it's going to grow based on how much there is now, not based on how much there was originally. So now, since there's more, it's going to grow more. And this exponential curve is going to continue as a curve instead of a straight line. This is exponential growth. Compound interest is one type of exponential growth. But before we talk about compound interest, we're going to talk about some other kinds of exponential growth. So in this situation, the price of gas is increasing. We know that. The price of gas, which started out as $3.20 per gallon, increased at a rate of 28% per year. Write the function that models this situation, substituting numerical values for A and R. Here they gave me the function or equation for exponential growth, just general exponential growth, not specifically compound interest. So here I have the function of x, or the total at the end, is the amount times 1 plus the rate to the power of x, which is going to be the amount of time. And what they want me to do in this particular problem is substitute a, which is the amount that I'm starting with, and r, which is the rate that it's increasing, into this expression. So f of x equals a, which is my amount that I started with. And in this case, it started at $3.20 a gallon. So I'm going to substitute that for a. 3.2. I could write 3.20, but after my decimal, any zeros that I have at the very end, they don't give me any new information, so I can leave them off or I can put them on. So I have a times 1 plus r. Same thing I was doing before with simple interest. I'm going to convert my percent. So right now r equals 28%. I'm going to convert that to a decimal. So I have r equals 28%. That's 28 per 100. I'm going to move my decimal place over 2 spaces, 1, 2. I'm going to move my decimal place over 2 spaces on the top, 1, 2. This time I don't have to hold that place with a 0 because I have digits in each spot. So my rate is 0.28. And I'm going to put that in, I'm going to substitute that or put it in place of r here. 0.28 to the power of x, which is the amount of time. Now, if I decided that I wanted to find out how much gas costs now after, let's say, 2 years, then I could plug that into my calculator. So this is not what they asked me to do in this particular problem, but let's go ahead and solve that. F of x equals 3.2. That's what it started out as, $3.20 plus 1 times 1 plus the rate, which is 0.28, to the power of the amount of time. And I'm going to say after 2 years. When I solve this equation, I'm going to use my calculator. On an iPhone, you can turn your calculator into a scientific calculator by literally turning it. Let's see if it'll try again. I've got to unlock my orientation. And by turning it, I made it into a scientific calculator. I'll move this up here so we can see. I'm going to use the order of operation to solve this equation. So in the order of operation, it says I need to solve parenthesis first. So I'm going to, every time I do a new step, I'm going to rewrite my equation. That way I can keep track, and if I make a mistake, I can look back and more easily see where it is. So f of x equals 3.2. That part is staying the same. I'm going to do my parentheses. So 1 plus 0.28 is going to be 1.28 to the power of 2. Order of operations tells me that I will do exponents next. I can do exponents 2 different ways on my calculator. I can use, because this is squared or to the power of 2, I can use the squared button, which is right here, x to the power of 2, or I can type it in and use this x to the power of y button, and I would put in my 1.2, which is my base, or the x, and to the power of 2. I can press this x squared button. That'll tell me it to the power of 2, f of x equals 3.2 times 1.28 to the power of 2 is 1.6384. The other way I can solve it is 1.28 and use this x to the power of y to the power of, and I'll type in the 2, to the power of 2 equals, same thing, 1.6384. And then finally I'm going to multiply by 3.2. So times 3.2. So after 2 years, gas that started at $3.20 is now $5.24, 0.288. And I'm going to round that because this is money. Probably your gas company is going to round up because they want more money. So they would probably round to $5.25. So if it's asking for you to tell how much gas costs now at the end of a certain period of time, then you would do these calculations. If the problem is asking you just to rewrite the function, substituting some particular variables, such as A, the amount you started with, and R, the rate, then you would stop here. This next problem says the expression f of x equals 215 times 1.042 to the power of x models the monthly growth of gym membership according to the function. What is the monthly growth rate? So in this particular case, we're going to be looking for R, the same R that we have in this exponential growth function. So I'm going to rewrite that function at the top of the problem. F of x equals A, the amount we started with, times 1 plus R, the rate, which is what we're looking for, to the power of x. So from this, when I compare these two functions, I know that I want to find the growth rate. That's this R right here. F of x equals, from this problem here, 215, the amount we started with. So that's like how many gym members they had at the beginning, times 1.042 to the power of x, however much time, or however many, because this is a monthly growth rate, however many months have gone by. Now, looking back at where I solved this previous problem, I can look and see in this particular part right here, I had 1 plus the rate, and that was equal to 1 plus 0.28, which equals 1.28. Here I have 1 plus the rate, and that equals 1.042. That's going to be my rate. So I know this section in parentheses here is equal to this section in parentheses here. So I'm going to write that as an equation that I can solve. 1 plus R equals 1.042. And I want to isolate R, or get R all by itself, so I know what R equals. So I'm going to get rid of everything else that's on this side of the equation around R. I want to get rid of 1. So I can subtract 1 from here, but only if I do it to both sides. If I only subtract R from this side of the equation, then it won't be equal to this side of the equation anymore. So I'm going to subtract 1 from both sides of the equation. And I took that away here. So 1 minus 1 is 0. I'm only left with r. R equals, here I have 1.042 minus 1. 1 minus 1 is 0. And I'm left with 0.042. So now I know my rate as a decimal, the monthly growth rate, is 0.042. I'm going to write that as a percent. Remember when we were changing a percent to a decimal, we move this decimal place over 2 places to the left. So to convert a decimal to a percent, I'm going to move this decimal place over 2 places to the right. So here I go, 1, 2. My new decimal place will be right here, and this is going to be 4.2%. So the gym membership is growing exponentially at a monthly rate of 4.2%. Now let's look at compound interest. Compound interest is a specific type of exponential growth. So it is doing this growth curve, this exponential growth curve, because the money that you started with, instead of the money that you started with earning the same amount every single time, it's earning interest on the principal, what you originally had, plus the interest that you earned during that compounding period, which might be a year, it might be a month, it might be every day. It's earning that percent of interest every time it increases. So each time, instead of increasing the same amount in a line or linear growth, it's increasing each time more in a curve or an exponential growth. This equation right here helps us find compound interest. It's very similar to the exponential growth equation, where f of x equals the amount we started with times 1 plus r to the power of x, where x is time. But they're using p because it's the specific name for the amount we started with. So p times 1 plus r divided by n. N is the number of times that it's compounding or increasing during each year. And then I'm also going to raise it to the power of n times t, the number of times I'm compounding each year times the number of years that the account is being held. So here, I'm going to say, and I can look back at my guided notes here in the section on compound interest. This is exponential growth, that same equation that was given before. And this is the equation specifically for compound interest, that expression. So same thing, p times 1 plus r divided by n to the power of n times t. So the question is asking us, what does each variable in the compound expression represent? So I'm going to go through each one. P, we talked about that that's the amount that we started with, and it has that special name of principal. Principal, that's the initial amount of money. The next variable I have is R. R tells me the rate or the annual interest rate. I'm going to skip over to T, which we've talked about before in simple interest. All three of these, principal, rate, and time, we talked about in simple interest. T tells me time, which is the number of years. I'm going to say how many years the account was held. And then we're going to look at N. N being the number of compounding periods. So the number of compounding periods in a year. So accounts compound at different numbers of times during the year. If the account compounds yearly or annually, then it would only be compounding one time per year. So if N equals 1, that means that it compounds annually or yearly. Sometimes it might compound more than once a year. So some ways that we can refer to that are if it compounds biannually, that would be twice a year. So N equals 2. If it compounds quarterly, you can think of 4 quarters in a game or 4 quarters in a dollar, 4 quarters in a year. N equals 4. It might compound more than that. Some other examples are if it compounds monthly. There are 12 months in a year, so N would equal 12. And if it compounds weekly, there are 52 weeks in a year, so N would equal 52. If it compounds daily, there are 365 days in a year, so N would equal 365. Let's look at a specific example using the compound interest formula. Let's leave this here so we can see it. This formula up above can determine the value of a savings account, actually this one, in 8 years. So if we put 8 in for T, then we could determine the value of this savings account. We want to know, what does each number in the expression represent? So we know that f of x, or the final value of the account, equals p times 1 plus r over n to the power of n times t. We can look at our compounding interest formula here or in our guided notes to find that out. So when we look at this specific example, then I can look back and see, based on what each of these things mean, what does this tell me about my account? So I know P is 1,500, and P is the principal. So the principal was $1,500, or they originally deposited $1,500 in the account. And then I can look at N at the bottom, the number of times that it compounded each year, and say that, thinking back, it compounded 4 times a year. And I see that same number here. So that means it compounded, we also call that quarterly. So I'm going to write that down. Compounded quarterly. And then the rate, which I'm going to have to do a little bit of calculation so I can put it as a percent. The rate was 0.01. I don't want it as a decimal though, I want it as a percent. And when I turn a decimal into a percent, I'm going to move this decimal point over 2 places to the right. So 1, 2, my new decimal spot is over here. So the rate was 1%. There we are there. Now we're going to look at 2 different accounts. The table shows the balance of 2 different investment accounts at the beginning of each year that the account was held. Assuming no other deposits were made, how can you describe the account's growth? So these accounts are only growing because of the interest that they're earning, not because of any money that's being put in outside of interest. I'm going to look first at this one because it's a little bit simpler than this one. So year 0, we're going to call that the principal. The account had $100 in it. From then, over that first year, they added $2 to the account from $100 to $102. The next year, they added $2 to the account from $102 to $104. And the next year, they went from $104 to $106. They added again $2 more to the account. So in this case, we see that every time the account is increasing by 2, increasing by 2, increasing by 2 in just a straight line. We call this linear growth. And I can calculate the rate that it's growing. Because this is linear growth, I know that it's simple interest. So to calculate the rate that it's growing, I'm going to use my simple interest formula, which is I equals principal times rate times time. And I can look back at my guided notes just like before and find that simple interest formula. There it is. Interest equals principal times rate times time. Then, to find out the interest rate, I'm going to plug in that information in each of the spots. So in the simple interest formula, it tells me just the amount of interest that was earned, not the amount total that's in the account at the end of that time. So the interest that was earned each time was $2. So I'm going to put that in for I. And the principal that they started with was $100. I'm looking for the rate. I don't know what it is yet. I want to find it. And I'm going to look over a period of just 1 year. So I'm going to put 1 in for time. So here I have interest equals principal times rate times time. Here, on this side of the equation, I can multiply this by 1. When I multiply anything by 1, it doesn't change what I have, it stays itself. So I'm going to rewrite this equation. 2 equals 100 times r. And then, to find r, I want to isolate r, or get it all by itself, get everything else away from it. Since I'm multiplying here by 100, I'm going to divide by 100, but I can't do it only on one side. I have to do it on both sides of the equation. So divided by 100. 100 divided by 100 is going to be 1. And when I multiply r by 1, it stays itself. It's just r. So the rate, r, equals 2 over 100. And I already know about percents that percent means divided by 100 or per 100. So then I can write my rate as a percent without moving any decimals or anything. It's going to be 2% per 100. Now, if I had to, I could calculate out 2, if I had another amount of principal on the bottom that wasn't 100 and didn't make this so easy. 2 divided by 100 equals 0.02. And to convert a decimal to a percent, I'm going to move my decimal over 2 places to the right. 1, 2, and there I have 2%. So now we look at this one. It's a little bit more complicated. They both start with the same amount of principal. They both start with $100. And after the first year, they both have the same amount of money. The first year, in this account, they added $2. Then from the next year, this account goes from $102 to $104.04. That's an increase of $2.04. And then the next year, it goes from $104.04 to $106.12. I can find the difference between these two by subtracting 106.12 minus 104.04, and I find that it increased $2.08. So instead of increasing the exact same amount each time, it's increasing more each time. Every time it increases more. So like we talked about before, this type of growth where first it grows by a certain amount and then it grows by a bigger amount and a bigger amount, this type of growth makes a curve, and this is called exponential growth. This growth is exponential, and we're going to use our compound interest equation for this. So, looking back at my guided notes, I'm going to find and write down my compound interest equation. P times 1 plus r over n to the power of n times t. F of x equals p times 1 plus r over n to the power of n times t. Now I want to find the the rate of growth for this account, just like I did here, but it is a little more complicated. Now, the difference between this simple interest calculation and this compound interest calculation, the simple interest is only telling me the amount of interest that they earned. So this on the side, they earned $2 each time. But the compound interest equation, the f of x, is telling me the total amount in the account after a certain period of time. So if f of x is the total amount, I'm going to say the total amount after 1 year, and that way my time will only be 1 year. That will be easier to calculate. So after 1 year, they had $102. The principal they started with was $100 times 1 plus the rate, which I don't know yet, I want to calculate, divided by n. In this case, the compounding period, I know how much is earned at the end of each year. So the rate I'm finding is for yearly compounding. So 1 time a year. I'm going to use that same number for n up here, times 1 year. After 1 year, this account had $102. So now I have a lot of ones to calculate with, which makes it a little easier for me. 1 in my order of operations, I'm going to look at the division right here. R divided by 1. If I divide anything by 1, it stays itself. So I'm going to rewrite this equation. 102 equals 100 times 1 plus r, that's a plus sign, to the power of 1 times 1. 1 times 1 is 1. Anytime I multiply by 1, it stays itself. And to the power of 1, anytime I raise something to the power of 1, it stays itself. So 1 plus r to the power of 1 is still going to be 1 plus r. 102 equals 100 times 1 plus r. Now, I have a variable here. I don't know what r is. And since it's a variable, a letter, not a number, I can't add it to 1. So in order to solve this equation here, I'm going to have to distribute this factor, 100, to each of the terms inside of my parentheses. So I'm going to multiply 100 times 1 and 100 times r, and then I can add those together. 102 equals 100 times 1, which is 100, plus 100 times r, which is 100r. Now, similar to the way I was solving equations before, I have to do, unless I'm simplifying this expression here, which is what I was just doing now, I have to do the same thing. If I change something, instead of just simplifying, if I change something on one side of the equation, I have to change it on the other side of the equation too, so that it will stay equal. So here, I want to get r by itself. The first thing I'm going to do to get it by itself is take away this 100. So I'm going to take away 100 on this side of the equation. So I have to make sure I take away 100 on this side of the equation as well. 102 minus 100 equals 2. 100 minus 100 equals nothing, 0. So I'm left with 100r. Now I still want to get r by itself, or isolate it. So I'm going to get rid of this 100 in front. How will I do that? Since I'm multiplying 100 times r, to get rid of it, I'm going to divide 100r by 100. Since I did it on this side of the equation, I have to also do it on this side of the equation. 2 divided by 100. 100R divided by 100. When I divide something by itself, I get 1. So 100 divided by 100 equals 1. 1 times R equals R. So here I have R, and here I have 2 over 100. So my rate is 2 over 100, or 2%. Here, since it's over 100, that's pretty simple to calculate that it's 2%, but remember, you can go back and watch how to convert to a percent if you have a decimal. So if they started with a different amount in their account, then you can divide this, 2 divided by whatever amount they started in their account, or whatever numbers you have, and then you would have a decimal, which you can convert to a percent. Let's look at this function now. I noticed that it is just like my compound interest function. And this function says f of x equals 1,300 times 1 plus 0.0125 divided by 12 to the power of 12 times t. This function models the balance in a savings account. What do you know about the account? So I'm going to compare here this function with my compound interest function. So the compound interest function says f of x equals principal times 1 plus r divided by n to the power of n times t. And I know, based on this right here, f of x equals 1,300 times 1 plus 0.0125 divided by 12 to the power of 12 times t. So I know one thing I don't know right now is t, how many times it was in the account, how many years. But I do know p, the principal. So the principal was $1,300, or the initial amount, the amount they started with, was $1,300. I also know R, the rate was 0.0125. Now, I don't want to express my rate when I'm calculating. I want to have my rate as a decimal. But when I'm talking about it, I want to have my rate as a percent. Remember, to change a decimal into a percent, I'm going to move my decimal point over 2 places and add that percent sign. So 1, 2, the rate was, my new decimal point is here, 1.25%. And then I also know n, the number of times it compounded each year. So the compounding periods compounded 12 times a year. And I will call that, because there are 12 months in a year, I will call that monthly. So it compounded monthly. And there we have it. I know a lot about this account, even without doing any calculations yet. The last thing we're going to look at here is effective annual interest rate. So when we have different compounding periods for an interest rate, different compounding periods, even if I have the same interest rate, if I have, let's say it's compounding at a rate of 2% yearly, I'm going to make more money if it compounds biannually instead of just yearly, or a lot more money if it compounds daily instead of just once a year. So I want to look and see, when I'm comparing two accounts that have compounding interest, I want to see not only what is the rate that they're compounding at, but how many times are they compounding each year. So that's called the effective rate. So the effective rate helps me calculate and compare different percentage rates that have different compounding periods. So thinking about if I had in this case, it's asking me, what is the effective annual interest rate on a savings account that earns interest at a rate of 2.03% compounded quarterly? Quarterly is going to be 4 times a year, so n is going to equal 4. I'm going to think about my compound interest equation. F of x equals principal times 1 plus the rate divided by n to the power of n times t. And I'm going to just think about, for any two accounts, if I put the same amount of money in, I would have the same principal, but this section would be different. So this section is telling me, based on that rate, that number of compounding periods and the amount of time that it's in the account. It's going to tell me how much that money is increasing. So I'm just going to look at that section of my compound interest equation. So I have 1 plus the rate divided by the number of compounding periods to the power of number of compounding periods times t. In this case, I know it's compounding quarterly, and I also know the rate that it's compounding. So I'm going to plug in those two numbers for my variables. 1 plus r, and here r equals 2.03%, or 2.03 per 100. To convert that percent to a decimal, I'm going to move my decimal place over 2 spaces to the left. 1, 2. My new decimal is here, and I need a 0 to save my place. So 2.03% is, as a decimal, is 0.0203. All right, so I'm going to put that decimal in when I'm calculating for the rate. 0.0203 divided by the number of compounding periods, which is quarterly, so that's 4, to the power of n, that's 4, times t. And now I'm thinking about the effective annual interest rate. So for 1 year, that would be annual. So that's just 1 year. I want to think about, what if n was 1 instead of 4? So in order to do that, I'm going to calculate this out and simplify this. I'm going to use my order of operations. And I'm going to use my calculator. In order of operations, it tells me to start inside the parentheses. And inside the parentheses, I'm going to look first at this division here. So 0.0203 divided by 4 equals see if we can get this all on here. Maybe not. Here. There we go. Okay. We have 1 plus 0.005075 to the power of, and I'm also going to do this, 4 times 1 is going to be 4. Anything times 1 stays itself. Now, I'm going to add 1 to this. I'm going to do what's in the parentheses. So 1 plus 0.005075 is going to be 1.005075 to the power of 4. And finally, I'm going to use my exponents button here because I only have to the power of 2 and to the power of 3 that I can just touch the button for. So I'm going to do this x to the power of y. I already have my base in here, so I'm going to press to the power of y. And the exponent y is going to be 4 equals 1.0204. There's a lot of numbers there. I'm just going to put 55. All right, so like I was saying, I want to know what would my rate be if n was 1, so an annual interest rate, instead of 4, which is a quarterly interest rate. So I'm going to look back at this little section. 1 plus r over n to the power of n times t. And I have this quarterly interest here as 1.020455. So I'm going to set these two equal to each other so that I can find my my effective interest rate, which is the interest rate when the compounding periods is just 1, it's annual. So I'm going to set these two equal to each other. 1 plus r over n to the power of n times t. And similar to what I did before, I'm going to put in 1, like I was talking about, as the number of compounding periods, and 1 as the number of years that it's compounding. And that's going to be equal to 1.020455. Now, I know that 1 times 1, anything times 1 is going to be itself. 1 times 1 will be 1. And anything to the power of 1 is going to be itself. So 1 plus r over 1 is going to be 1 plus r over 1. So 1.020455 is going to be equal to 1 plus r over 1. I also know anything divided by 1 is going to be itself still. So r divided by 1 is going to be r. So 1.020455 is going to be 1 plus r. So what I'm going to do here is subtract 1 from both sides, just like we talked about before. If you do something to change, not just simplify, but change one side of the equation, you have to do it to the other side of the equation. So I'm going to take r away on this side, and I'm going to take r away on this side, and on this side I am left with just r. 1 minus 1 is nothing, so I have nothing but r left. So on this side I have just r, and r equals 1 minus 1 is 0, so I have 0.02045. I'm going to convert this from a percent to a decimal, and remember to do that. We're going to move our decimal point back 2 places to the right. 1, 2. And so our rate quarterly was 2.03%, and that's an effective annual rate of 2.04%. And then we can compare that to other annual interest rates because they're compounding the same number of times each year. And that's what we're going to do here. We're going to compare annual interest rates in these accounts. I have 3 accounts here. Account 1 is compounded annually at a rate of 3.15%. Account 2 is compounded semi-annually at a rate of 3.05%. Account 3 is compounded monthly at an, that's not what I meant to say, at a rate, this is the compounding rate, I'm sorry. Okay, it's compounded monthly at a rate of 2.75%, and this one, account 4, is compounded quarterly at a rate of 2.25%. All right, so I'm going to split my paper into 4 sections for each of the 4 accounts. And I have account 1, account 2, account 3, and account 4. All right, looking at account 1 first. Account 1 is compounded annually. That means the number of times it compounds per year is 1. So 1 plus r over n times to the power of n times t. All right. Just like in the previous problem, we're just looking at this section of my compounding interest equation. And I'm going to plug in what I know from account 1. For account 1, the rate is 3.15%. 3.15 per 100. I can convert that to a decimal by moving the decimal point over 2 places. So my new decimal point, 1, 2, I have to put a 0 to hold that place. My new decimal that equals the same is 0.0315. I'm going to put that in for r over here. That's my rate, 0.0315 divided by the number of times it compounds is n equals 1. 1 time per year because it compounds annually. And I'm going to put that same number up here for n there over a period of 1 year I'm looking at. So I'm going to go ahead and calculate here. Bring the calculator over. Order of operations says I'm going to do parentheses first, and the division inside the parentheses is 0.0315 divided by 1. Anything divided by 1 is itself, so I have the same thing, plus 1. That's what I have inside my parentheses. So I have 1.0315 to the power of 1 times 1, that's going to be 1. So anything to the power of 1 is going to be itself still, so 1.0315. And just like I did up above, when I was finding that rate again, basically I just subtracted 1. That's what I did. So I'm going to do that same thing here. I'm going to subtract 1 to find out what the rate is. 0.0315. In order to convert this decimal to a percent, I'm going to move this decimal place over 2 spaces to the right. So my rate will be 3.15%. Now, I didn't really have to do all those calculations because they already told me this was the annual rate. And that's what I'm trying to find for each of these is that annual rate, the annual rate of 3.15%. But I'm going to do those same things for accounts 2, 3, and 4, where I don't know the annual rate, except that I accidentally wrote that down. But this is going to be the rate that it's compounded semi-annually, not the annual rate. That was an accident. But if you know the annual rate, then you can already compare that effective annual interest rate, because what you're comparing when you're comparing effective rates is what it would be if it only compounded 1 time per year. All right, so here for account 2, we're going to do this same calculation. Account 2 is compounded semi-annually, so 2 times a year, n equals 2. And my rate here is 3.05%, 3.05 per 100. Move that decimal place over 2 spaces to convert my percent to my decimal. Now, if you just remember to convert a percent to a decimal, move the decimal point over 2 places to the left. To convert a decimal to a percent, move the decimal place over 2 places to the right. You don't have to write down this per 100 divided by 100. That's just to help you connect that percent to divided by 100. So if you forget which way or which one, you can do this. You can even plug it into your calculator to double check it if you forget which way the decimal moves. But if you remember, then converting a percent to a decimal, you're going to move that decimal over 2 places to the left. 0.0, I have a 0 to hold my place here, 305. And I'm going to put that in for my rate here. So 1 plus 0.0305 divided by n, the number of compounding periods, semi-annual, 2 times a year, and I have that same number up here, times 1 year. So I want to find out what that rate would be for 1 year. So I have 1 plus, I'm going to go on my calculator and divide this out. 0.0305 divided by 2 equals 0.01525. Oh, you cannot see that. There it is. To the power of 2 times 1 is 2, so to the power of 2. So for account 2, I'm going to add this together. So 0.01525 plus 1 equals 1.0125 to the power of 2 equals 1.0307, that's an awkward 3, 325. We're going to stop there. This is a 3. All right, so I added these and then I put it to the power of 2. Then, just like I did over here, I'm going to subtract 1 so that I can find that rate over 1 if it was 1 compounding period per year. So minus 1, I'm left with 0.0307, so on. I'll add a 3 there. I'm going to move my decimal place over 2 places to the right to convert my decimal to percent. So 1, 2, 3 point. I'm going to round to the 2 decimal places, so 3.07%. 3.07%. I can leave it at 7 because this number next to it is less than 5, so I'm rounding down. 3.07%. Do the same thing for account 3. 1 plus my rate here. This account is compounded monthly, so the compounding periods equal 12, and my rate here equals 2.75%. Move that over 2 decimal places, 2 decimal places, 0 to save my place. My rate is 0.0275. 0.0275, that rate divided by the number of compounding periods. This is compounding monthly, so that'll be 12 to the power of 12 times 1 year, because I want to find out how much that compounding rate would be for 1 year. All right, so here I go. 0.0275 divided by 12 equals 0.00222916, so on. I'm just going to add 1 on my calculator. So plus 1 equals 1.00229 to the power of 12 times 1 is 12. And I'm going to use that to the power of button, exponent button, to the power of 12 equals 1.0278. 1.0278. Just like I did over here, I'm going to subtract 1 so I can find my rate if the compounding periods were only 1. So minus 1 is 0.0278. And to convert that decimal to a percent, I'm going to move that decimal place over 2 spots. 2.78%. And this would be 784. So because this is less than 5, I can round down or stay the same. Now for account number 4, this interest is compounded quarterly or 4 times a year, so n equals 4, at a rate of 2.25. So the rate is 2.25%. Move that decimal place over 2 spaces. And in this case, I need a 0 to hold that space. So my rate as a decimal is going to be 0.0225. I'm going to plug this into my equation 1 plus 0.0225 divided by n, which here is 4, to the power of n, which is 4, times time, which is for 1 year. Same thing, I'm going to use those order of operations to solve this. So I have 0.0225 divided by 4 equals 0.005625. And I'm rewriting my equation so I don't miss any steps. Plus 1. So now I have 1.005625 to the power of 4 times 1, which is going to be 4. So to the power of 4 equals 1.022690. Just like before, I'm going to subtract 1 so I can find my rate if this had only 1 compounding period a year. So I have 0.022690. I'm going to move my decimal place over 2 spaces to make it a percent. My percent effective annual interest rate is 2.2, and this time I have a number that's bigger than 5, so I'm going to round up. So 2.27%. Now I can compare. This tells me if all of my accounts compounded only annually, what would my percentage rate be? For account 1, it's 3.15%. For account 2, it's 3.07%. For account 3, it's 2.78%. And for account 4, it's 2.27%. And this lets me compare which one will I get a better interest rate, because I know the effective annual interest rate, what percent it would compound at each year compared to what percent it compounds at each month. All right, and that's our review.